Alright, so in this video we go over section 11.5, partial fraction decomposition. So the purpose of this section is mainly to do a problem that we have done in algebra, which is combining fractions together, but we're going to do it backwards. So first of all, let's find out how would we combine these two fractions together. And well, in this case, all we do is, well, in the case in which the two denominators are the same, well, we just keep the denominator and add or subtract depending on the operations with the numerators. But in this case, these are two different denominators, so we need to find a least common denominator. In this case, well, since both of them are different, we need to actually find an LCD. It's going to be the product of the two. Alright, so in this case we would need to multiply by missing factors. The missing factors are each other's denominators, so x plus 2 over x plus 2, x plus 2 over x plus 2. Okay, so now that we have the same denominator, all we do is write a big fraction with the LCD below and multiply across 2 times the quantity x plus 2 plus 4 times the quantity x plus, actually this is supposed to be 4, not 2, and so this is 4 and x plus 2. So what are we going to get? Well, distribute, you might want to apply to x plus 2 times 4, which is 8, then plus 4x plus 8 as well. And all we do in the numerator is combine like terms. So in this case, x's with x's, that's 2x plus 4x, that's a 6x, and x plus 8, that's a 16. And we can leave it like this. I know we can factor out a 2 from the numerator, but that's not going to help at all. In the sense of simplifying the fraction. Alright, now, the purpose of this lesson, of this section rather, is reverse this process. Given a big fraction together, write it down into simple fractions or partial fractions. Right, and that's what this topic is about, and we are going to consider 4 cases when all the denominators are non-repeated linear factors, when the denominator has repeated linear factor, and then the other 2 cases when the denominator has non-repeated, but in this case irreducible. Actually, these are supposed to be quadratic factors, and repeated irreducible quadratic factors. We're going to do one of every single case. You'll see the difference. So let's do one simple one. Well, so consider the denominator in which that can be factored as x minus a number, or plus, well, depending. But in this case, all different factors in the denominator are distinct. So we're going to have our big fraction, and we're going to turn this into a number, or rather a letter to be found in this case. Well, here we're going to have a1, a2, a3, blah blah blah, but in this case, in the practice, we're going to use the letters a, b, c, d, etc. All right, and those fractions are to be determined. So this is the definition. Well, it doesn't really have any numbers really, so let's just go over one example. All right, so to begin with, let's do the one that we have that we did in the example. So the 6x plus 16 divided by x squared plus 6x plus 8. Well, in this case, the denominator is not in factor form. Let's first of all factor it out. Well, so 6x plus 16, and we're going to factor out this trinomial. Well, we're going to look for factors of 8 that add up to 6. In this case, that's a plus 2 and plus 4. pretty much what we obtained from the backwards exercise. And then the next step right here is to do the following. Well, you might want to ignore for a while, for a second, the numerator. Just call it a over the first factor plus b over the second factor. And in this case, well, we are going to determine these two constants. Well, how do we do that process? Well, so what we do is I'm going to copy these two last steps and I'm going to turn that into an equation. I'm going to do it here. 6x plus 16 over x plus 2 times x plus 4. And that equals to a over x plus 2 plus b over x plus 4. Okay, so that's what we do here. So we're going to multiply both sides by the LCD. So the LCD in this case is the product of these denominators, this x plus 2, x plus 4. So we're going to multiply both sides by x plus 2, x plus 4. On the other side as well, x plus 2, x plus 4. All right. So what are we going to do in this case? Well, so on the one hand, when we distribute here, and we distribute, these two just go away. These two just cancel. And in this case, we're going to be left with 6x plus 16. And then on the second side, on the other side, what we do is distribute these two factors over the first fraction. But when we do that, these x plus 2's cancel, leaving us with a times x plus 4. And last but not least, when we distribute over this last expression, this b over x plus 4, it is the x plus 4's that go away, leaving us with b times x plus 2. All right. So we are going. This equation is what we call our basic equation. From these basic equations, we are going to obtain our unknowns a and b. This is typically the easiest case to work with, because in this case we can use the opposites of these numbers to find the constants a and b, because I'll show you on the process why that works. But in this case, this method only works for non-repeated linear. In the other methods might work, but might help, but not for much. So here we're going to look for a way to turn this term into a 0 and to be able to find b, and then we're going to look for a way to turn this term into a 0 so we can find the unknown a. So for example, in this case, if x equals to -2, what do we obtain? Well, so this is going to be 6 times -2 plus 16 equals to a times -2 plus 4 plus b times -2 plus 2. So let me put the -2 with the correct color. So what's going to happen? -2 plus 2, that's going to be a 0. So this zeroes out. And we're going to get, well, 6 times -2, that's -12 plus 16 equals to 4 minus 2, that's 2 times the quantity a. So the x's disappear and the b disappears, so we will be able to find the value of a. So 16 minus 12, that's going to give us 4. And dividing both sides by 2, a equals to 2. So a will be 2. Let's do the same now to cancel the a term. So in that case, what we do is, if x equals to negative 4. Well, so that's 6 times negative 4 plus 16 equals a times negative 4 plus 4 plus b times negative 4 plus 2. So let's put the negative 4, negative 4, negative 4. So 6 times negative 4, that's a negative 24 plus 16 equals, well, notice in this case, negative 4 plus 4, this whole term goes away. All right. And negative 4 plus 2, that's going to give us a negative 2b. So the rest is just solving this baby equation for b. Right, that's let me make it look like a b. That's a b. So negative 24 plus 16, that's negative 8 equals negative 2b. And then divide both sides by negative 2. That's going to give us b equals to positive 4. All right. So now we're going to bring these two constants right here and put them here. So final answer, a, which is 2 over x plus 2, plus b, which is 4 over x plus 4. And that's exactly the original problem we were given at the beginning of the section. So now we just learned how to do the reverse of combining these two fractions, which in this case is partial fraction decomposition. All right, now what happens when we have repeated linear factors? For example, one of the factors in the denominator is of the form x minus a to the n. I don't know, maybe some x minus 3 squared or cubed. So how do we deal with those? Well, the decomposition, we are gonna write all powers from 1 to n and write the corresponding partial fraction for each of the terms. So how is that gonna work? Well, let's see. So number one, for this one, well, we have x plus 2 divided by x cubed minus 2x plus x. So we need to make sure that these fractions are the denominators of these rational expressions are in factor form, at least the denominator, because that's where we're going to determine whether we have linear factors or quadratic, and if quadratic irreducible or repetitions of them. So in this case, let's factor the denominator as x times x squared minus 2 x plus 1, and all under x plus 2. Okay, and then, well, so x, in this case we can still further factor this quadratic factor. So x squared minus 2x plus 1 factors of 1 that add up to negative 2. Well, that's x minus 1 times itself. But in this case, you might want to rewrite this in a slightly different form. I'll show you how. So in this case, let's see. I'm going to write this as x plus 2 in the numerator and x times x minus 1 quantity squared. All right. Now, how is this going to work? Well, so I'm going to assign a letter A for the first factor x. And notice the factor x minus 1 is repeated because we have it squared. It would have been repeated as well if we had it to the third power. Then we would have a repetition by 3. And if we were a fourth power, it would be repetition by 4, etc., etc. So plus b over x minus 1, well, that's the first power, and c divided by x actually minus 1 squared, and we stop there. Again, if we had this to the fourth power, for example, we would have written x minus 1, and then x minus 1 squared, and then x minus 1 to the third, and then so on all the way to the fourth power. Alright, so just like we did it in the previous example, I'm going to rewrite these two steps right here. And what am I going to do? Well, so first I will copy them again. X plus 2 over x times x minus 1 squared equals to a over x plus b over x minus 1 plus c over x minus 1 squared. And we're going to multiply both sides by the LCD to clear the denominators and obtain our basic equation here. Alright, so what are we going to have here? Well, so when we distribute this to over here, pretty much everything here goes away, that cancels, and we are left with x plus 2 equals, and then in this case, well, so I'm going to multiply this, I'm going to distribute, and in this case, notice how the x's go away, leaving us with a times x minus 1 quantity squared. When I do this same thing over here, this x minus 1 cancels with 1 power here, leaving us with x times x minus 1 times b. Okay. And last but not least, for the last part of the distribution, this x minus 1 squared cancels with x minus 1 squared. And that's going to leave us with c times x. Alright, what are we going to do here? Like I mentioned earlier, finding a way to zero out some of the factors is not going to work. Well, it might work in a way, but it's not going to work fully. So we're going to take an alternative route in this case. So this is what we're going to do. We are going to expand all this. We'll have to expand all this, so that's x plus 2 equals to, well, this is a binomial squared whose expansion is x squared minus 2x plus 1. Either FOIL it or simply bring it from the fact that this guy came from factoring this trinomial. And then in this case, plus, okay, bx times x, that's going to be bx quantity squared, then the quantity bx times -1 minus bx. And then finally plus cx. Alright, so I'm running out of space here. Let's move to the next page. I'm going to have this on the top so we can refer to what we're doing. Okay, so I'm going to continue down here. We'll continue on the next page. So in this case, I'm going to distribute the a over the 3 terms here. So that's going to give us x plus 2 equals to ax squared minus 2ax plus a plus bx squared minus bx plus cx. Okay, and then what we are going to do, so we are going to put together the squared terms and then the linear terms, that is all the terms that have x to the first power, and then the constant terms together. So how are we going to do this? Well, x plus 2 equals to, well, I'm going to factor this together times x squared, but what is going to go inside? Notice we have some a plus b. Okay, let's do the same with x coefficients. Well, so we're going to have a negative 2a minus b and then plus c. And last but not least, well, that's going to be plus simply a. Okay. So now, what are we going to do in this case? Well, number one, we're going to do what we call equating coefficients. So, for example, we have coefficient of x squared, coefficient of x to the first, and constant term. So, what we're going to do? Well, I think the easiest to visualize here will be this one. Well, notice the coefficient of x here is an invisible one. All right, because that's just x, and it's understood to have a 1 as a coefficient. So because this is an equation, this coefficient is the same as this coefficient, this whole thing. All right, and that's what we're going to set in a minute. And then for the constant term, we are simply going to say that this constant is equal to that constant. In other words, a equals to 2. And then what about the square terms? A plus b, it's going to be equal to what? Well, so you might want to add, in this case, as a trick, add a placeholder, 0x squared, So it's not there, but we can put it in there as a coefficient of x. And in this case, well, let's equate the coefficient. 0 equals to the quantity a plus b. And from there, we are going to set a system of equations. Well, how is that system going to look like? Well, a plus b equals to 0. Negative 2a minus b plus c equals to what coefficient? 1. And last but not least, a equals to 1. A equals to 2, rather. All right. So you might be thinking, well, should we use matrices or elimination? Well, in this case, it's not a big deal. It's not a big deal because we can, in a way, substitute a equals 2 to find b. And then once we get this b, we can plug in a and b to finally find c. So a equals 2, that's done. So let's use a plus b equals to 0, plug in a equals to 2. So 2 plus b equals to 0, b equals to negative 2. So that's one solution, that's another solution. And then we're going to use the second equation, negative 2 times a, which is 2, minus the quantity b, which is negative 2. Be careful here with the signs. And plus c equals to 1. And all we do again, we're going to use a smile rule here. Smile, be positive. Negative 4 plus 2, that's a negative 2 plus c equals to 1. And adding 2 to both sides gives us c equals to 3. All right, so we have the three constants, a equals 2, b equals to negative 2, and c equals to negative 3. So going back to the problem, to the original problem here, let me just go back to the previous page really quick. All right, so we can see a, b, and c. We can continue here. Our final answer is 2 over x minus, because b is a negative number, 2 over x minus 1. And then plus c equals to 3, which is the denominator x minus 1 quantity squared. Of course, how do we check if this is right? Well, do this combination of the three fractions. In the end, you should obtain the original problem. All right, so that was another example. In this case, an example with the second case. Now let's look at case 3, where the denominator has a non-repeated irreducible quadratic factor. All right, so in this case, the numerator that correspond to those kinds of of denominators are going to be a linear factor of the form ax plus b, or the corresponding letter in the alphabet, depending on how many how many factors do we have. So first of all, before explain, this one is going to make more sense once we look at the example. So in this case, what do we have? We have 3x minus 5. And then in this case, we can factor the denominator because we have x cubed minus 1. So you might want to recall one of the special factoring products, that's in this case the difference of cubes. Let me write down the formula just so you can recall this one. So that's a squared, ab, b squared. So we have the same sign, the opposite, and that's always positive. All right, so that's how we are going to factor this one out. Well, so what are we going to do in this case? So in this case, this is going to be x minus 1 times the quantity x squared plus the product of these two, which is 1 times x, that's x, and plus 1. All right? And in this case, well, this is a linear factor, x minus 1, and this is a quadratic factor, but this is an irreducible quadratic factor because, number one, if you try to factor this trinomial right here, you will be looking for factors of 1 that add up to 1, and those are impossible to obtain. And on the other hand, if you try to solve this, if you try to get the roots of this polynomial using the quadratic formula, and you might want to do, I'm not going to do it, so it's not part of the topic in this case. But if you want to do it on your time, you'll find out that the solutions to this equation that will give us the factors are going to be complex numbers. And in this case, we're looking for only real numbers, not complex numbers. So in this case, well, the first factor, x minus 1, will have a constant a in the numerator to be determined. And the quadratic irreducible will have a linear factor in the numerator, that is bx plus c. In this case, notice I didn't use ax plus b because, well, that's what corresponds in the alphabetic order. Now, notice in the previous example. So let me show you. In this case, just so you can connect the different the idea of the different unknowns that we assign. What is the degree of this denominator? Well, the power is 1. That means it's degree 1. So in this case, the numerator is 1 degree less. Well, there's no variable. Well, not really, because that's like x to the 0. So the degree is 1 less than that in the denominators. Same here, x to the 0, x to the 0. But we don't write those x to the 0. All I wanted to say here is that degree 1, linear is degree 1, the numerator is 1 degree less, which in this case is degree 0, or simply constant. For this case, well, for this case, linear again corresponds to 1 degree less, which is degree 0. Quadratic corresponds to 1 degree less, which is degree 1. So that's the main takeaway here. You might want to keep in mind. All right, so we're going to proceed to do the rest of the process. Okay, again, I'm going to copy these two to get the basic equation. So I'm going to write 3x minus 5. I know it's just rewriting it. Yes, I know it's going to be a little bit tedious. And that equals to a over x minus 1 plus bx plus c over x squared plus x plus 1. And in this case, what do we have? We need to multiply by the LCD, which in this case is the product of these two, x minus 1, x squared plus x plus 1, x minus 1, x squared plus x plus 1. So we are going to do the distribution here, and in this case, what do we get? So multiply, these two cancel out, and goodbye. All right, so let's see, what are we going to get? 3x minus 5 equals to, when we distribute over here, multiply times a, x minus 1 with x minus 1 cancels. We are left with a times the quantity x squared plus x plus 1. All right, and when we distribute finally for the last factor, we're going to cancel out these trinomials, and we're going to be left with the quantity bx plus c times the quantity x minus 1. All right, so this one is going to take a couple of distributions, not that much. All right, so 3x minus 5 equals to, I'm going to distribute this as ax squared plus ax plus a. And then in this case, so let me just indicate what was done. Distribute, distribute, and distribute. And in this case, we would have to FOIL this, bx times x and bx times negative 1, giving us bx squared minus bx. And last but not least, c times x, c times negative 1, giving us the quantities cx and minus c. And what are we going to do over here? Well, the same process that we did in the previous example, which is equate coefficients. So let's use the other side of the page, the next page actually. And this is going to be, in this case, let's group all the squared terms. So squared times square, square and squared, right? And then linear with linear with linear, and that's going to be constant with constant. So this is what we do. So 3x minus 5 remains the same on the left hand side, and we open parentheses and we put together all the coefficients of x squared. So that is a plus b. And then a plus b rather, and then plus, in this case, all the linears, in this case, that's a plus minus b and plus c. And times x, and then plus a minus c. Okay. And what are we going to do? So in this case, we are going to be in the need of adding that placeholder, 0x squared. All right, and that's because, well, so we're going to do the same combination. 0 equals a plus b, because the coefficient of x squared equals the coefficient of x squared, because this is an equation. So from here, we're going to write a plus b equals to 0. And then the coefficient of x, which is 3, must be equal to that coefficient here. All right, this entire expression, that is, in this case, a plus b minus c. And that equals to 3 in this case. Okay, last but not least, for the equating coefficients, the constant term, which is negative 5, equals to the constant term a minus c. So in this case, a minus c equals to 5. Alright, so in this case, well, there's no way to eliminate variables like we did in the first, in the previous example, not the first one, that was the previous example. So in this case, we need to find to choose a method to solve this system of equations that depends on 3 equations and 3 unknowns. Of course, you can use the elimination method, but that's going to take a while. You might want to use matrices by hand. That's going to take a good minute as well. Even the determinant method, which is the Cramer's rule rather, that's also going to take a while because we would need to evaluate 4 determinants that are 3 by 3. So in this case, yes, I'm going to use matrices, but you know how to use your graphing calculator, all right? So we can use, in this point, you can use your graphing calculator. You don't have to do it by hand. 1 minus 1, 1, 3, and 1, 0, negative 1, negative 5. All right, so I'm just going to give you the solution to this system. Just do RREF on your graphing calculator. You should get 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the solutions to this are going to be a little bit funky. 2/3, negative 2/3 actually, and then 2/3 and 13/3. Actually, when you do the RREF on your graphing calculator, you're going to get decimals in the first place. When you change those decimals to fractions using the frac command. All right. So that means in this case that from here this is A, from here this is B, and from here this is C. So let's go back to our original problem in this case. So on the previous page, that is equal to A, which is negative 2/3 over x minus 1 plus 2/3 x plus 13/3 over x squared plus x plus 1. And that's our final answer to this exercise. All right. Let's do the last case, case 4. So case 4 in which the denominator has repeated, but in this case, quadratic irreducible factors. So how do we deal with them? So just like we did with the linear factor, we put all the powers just the same way we did in this case. So in this case, by the way, this one should be, it's not a 4, that should be a 2. Otherwise, it's gonna get a huge disaster here. That should be squared. All right. So, well, in this case, if we try to factor x squared plus 4, well, it's not going to be factorable over the real number system. In fact, this would factor, well, if you recall previous chapters, that'll be x plus 2i, x minus 2i, and x plus 2i. And we're not looking for complex or imaginary numbers. So what we do in this case, well, simply x squared plus 4, all right, and x squared plus 4 quantity squared. And in this case, because we have it to the second power, if this power were a 4, for example, we would have wrote another fraction with the denominator x plus 4 to the third, and then one more with the denominator x squared plus 4, but to the fourth power, all the way to the highest power that we see, because in this case, the highest power of this irreducible quadratic factor is 2. We write the power 1, invisible 1, plus the power 2. The numerator, ax plus b, cx plus d. In this case, we are going to determine 4 numbers, right? 4 unknowns. I know that's going to sound a little bit crazy. Maybe you are foreseeing a huge disaster with an equation of 4 equations with 4 unknowns. Well, that is true. There will be 4 equations and 4 unknowns, but it's not going to be as bad as you might be thinking. So, in fact, it looks like case 4. It's going to be the most complicated of the 4, but it's not as bad as you'll see. So let me rewrite again, copy, so we can obtain the basic equation to find the unknowns. Quantity squared, and multiply both sides by the LCD. The LCD here will be the product, well actually, well not the product, x squared plus 4, quantity squared, x squared plus 4, quantity squared. Alright, so let's go ahead and do this. Well, when we distribute here, x squared plus 4 quantity squared, x squared plus 4 quantity squared, both go away. That's x cubed plus x squared equals to, and on the left hand side we are going to have, we multiply the first factor when we distribute, this guy which is to the first power going to cancel with 1 power, leaving us with 1. So we're going to get x squared plus 4 to the first times the quantity ax plus b. So ax plus b times x squared plus 4. And then this is plus, let's do the last one. When we multiply, notice how these two are going to cancel the 2, leaving us only with cx plus d. And in this case, well, you know the drill as from the previous examples. Well, all we do is keep simplifying to equate coefficients. So that's going to be ax times x squared, ax times 4. So that's going to be ax cubed plus 4ax. Okay, and one more distribution, bx squared and b times 4. So bx squared plus 4b. Don't forget this cx plus d. And the left hand side remains the same, x cubed plus x squared. Alright, time to equate coefficients, but notice in this case these go all the way to the third power. Well, that's only 1. And then second power. And then do we have linears? Yes, we have linears. We have a first degree. That's what we mean by linears. And one different color, orange, don't die on me. All right. Well, it's almost similar to this yellow shade. Well, let me actually make it a wiggle here. Yeah, just to make it different. All right, so a times x cubed plus b times x squared plus, in this case, for the powers of x, in this case we're going to have 4a plus c. And for the constant terms, we're going to have 4b plus d. Alright, be careful with cases like this, because if you observe the left hand side, we only have the x cubed term and the squared term. But what about the linear term and the constant term? They are not there, but they are there if we will, but in this case we need to make them phantom. You know, x cubed plus x squared plus 0x plus 0, you know. 0x is 0 plus 0 is 0 plus whatever quantity, in this case x cubed plus 2, x cubed plus 2. But we add these placeholding terms so we can equate coefficients. And with the equating of the coefficients, that I'm going to do it over here. All right. So let's see. Let's put all these together. And in this case, this is a 1 right here, an invisible one, another invisible one. That means A equals to 1. Okay, so see why this system will be easier than we anticipated earlier. Yes. 1 equals to B. That's another giveaway, another given rather. Another freebie. And in this case, what are we going to have? That's 0 time equals to 4a plus c. That is 4a plus c equals to 0. And last but not least, let me look another color here. Hopefully this works. 0, that's also like pink, but it was supposed to be purple or so. And that's leading us to the equation for b plus d equals to 0. Yes, we have 4 equations, but actually in this case 2 are knowns, a and b. Okay, so what are we going to do in this case? So 4a plus c equals to 0, 4b plus d equals to 0. We are going to use a, substitute it here to find c. And then we're going to plug in b equals 1 here to find d. Really simple. Way simpler than we anticipated actually. Alright, so 4 times 1 plus c equals to 0. 4 plus c equals to 0. c equals to negative 4. And same for b, but I'm going to do everything. 4 times 1 plus d equals to 0. 4 plus d equals to 0, and d equals to negative 4. Alright, so now that we have a, b, c, and d, so let's go back to the original problem. So let me make some space here to this one. A, we said a equals to 1, b equals to 1, negative 4, and negative 4. Well, of course, I'm not going to leave it like this. I'm going to actually write the final answer. Let me make some room here. So this will be x plus 1 that divides x squared plus 4, because that's a 1x plus 1, plus negative 4 x minus 4 divided by x squared plus 4 quantity squared. And we can leave it like this, that's fine. Or maybe you might want to factor out the negative sign, leave this into a positive, and then change that positive into a negative. But I'm pretty sure my MATLAB is going to take either answer. Alright, so let's do one more example. You know, one of those setup type of problems, but we're not going to fully solve. This is just to basically summarize what we did today. So let's have a look at this. Number 1, okay, what kind of factors do we have? Yes, it's crazy and we have too many. If we had to do this solving of this system, is going to be really crazy, which is not what we're going to do. So this is non-repeated linear. I'm going to use NL for non-repeated linear. And then x plus 7, we don't see another x plus 7, that's a non-repeated linear. And x minus 1 cubed, well, that's repeated 3 times, that's a repeated linear. Okay. And then x squared plus 16, that's not factorable over the real numbers. So in this case, this is a quadratic, but in this case, non-repeated quadratic irreducible. X squared plus 7x plus 1. Well, if we try to find factors of 1 that add up to 7, well, what are we going to have in this case? what we're gonna have in this case, it's not possible to find factors of 1 that add up to 7. But notice it's to the second power, so this is repeated quadratic. X squared plus 9 to the fourth power, that's also repeated quadratic irreducible, because x squared plus 9 has no solution over the real numbers, and we also have it to the fourth power. How is this going to look like? Crazy? Yes, it's going to look big. So the first factor, x minus 4, the constant to be determined would be a, plus b divided by x plus 7, plus c divided by, in this case I'm going to go all powers of x minus 1. X minus 1 to the first, x minus 1 to the second, x minus 1 to the third. Alright, and we stop there. What about the x squared plus 16? So x squared plus 16. Alright, that corresponds, so that's E, that's F, x plus g, and then plus, notice the x squared plus 7x plus 1. We have 2 powers of each, so f, g, h, x plus I, and then plus, well, I'm gonna go over here. Now let me go over here. X squared plus 7x plus 1 quantity squared. All under, okay, j x plus k. Alright. And then we're gonna do 4 more fractions for this x plus 9 to the fourth power. That is plus x squared plus 9. So that's lx plus m plus x squared plus 9 quantity squared nx plus o plus x squared plus 9 to the third power, px plus q, and then x squared plus 9 to the fourth power, and that's rx plus s. We almost covered the entire alphabet. Interesting. But yeah, so I mean, combining all cases together, suppose you would have some huge problem like this. This is how you would be breaking it up into all simple fractions. Yes, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 variables to find out. Huge system. Of course, is it possible to do it? Yes, most likely we would have to use a computer like MyMathLab or Maple to solve that system of equations, but it's not impossible. Yes, it's gonna be really, really hard, or simply another alternative, put this on an algebraic solver system or something. But I mean, the idea of doing an example like this, which is just the setup, not the solving, is so you can have a better overview of what we did in the previous 4 examples. So you can expand so you can see this in an expanded form. What else can be done? Alright, so I think this is a good place to quit. So this is the end of this section. I'll see you in the next video.